In this video, we're going to introduce one of the more famous theorems known as the Fundamental Theorem of Algebra. So let's start with a definition here that talks about basically how many times a linear factor divides a polynomial. So let's say that we have c is a 0. Then we say that c has multiplicity m if x minus c to the m is a factor of p of x, or divides p of x. But if I add one more factor, then it does not divide it anymore. All right. So that's a lot of words, a lot of symbols. Let's see if we can illustrate what we mean by this through an example. So let's suppose p of x is the polynomial that's already been factored. It factors as x plus 3 squared times x minus 5 times x minus 8 to the 5th. Now we can read the zeros pretty easily once we put it in factored form. It's the whole point of trying to factor these things. The zeros are negative 3, 5, and 8. Pretty straightforward to see that. Now, looking at the exponents on each of these factors that gave us those zeros, give us the multiplicities. So negative 3 has a multiplicity of 2. 5 has a multiplicity of 1, and 8 has a multiplicity of 5. So the multiplicity ends up telling us a couple of things about the graph of the polynomial. Okay? First thing is that if m is odd, then the graph actually goes through the x-axis at the 0. If the m is even, then the graph just touches the x-axis and turns around in the same direction it came from at the 0. The second thing here that we have that it tells us is that if the multiplicity is greater than 1, then the graph actually flattens or out at the 0. Alright, so let's go back to the previous example. We had the zeros of negative 3, 5, and 8. Those correspond to the x-intercepts of negative 3, 0, 5, 0, and 8, 0. Now the multiplicity of x minus 5, the multiplicity of 5 is 1. That's an odd multiplicity, so the graph would cross the x-axis at 5. The multiplicity of 8 is 5, which is also odd, so the graph will cross the x-axis at 8. Now, the multiplicity of negative 3 is 2. That's an even multiplicity, so that means that the graph turns around, touches the x-axis and turns around at negative 3. Furthermore, since these multiplicities at negative 3 and at 8 are bigger than 1, the graph flattens out at those two x-intercepts. It does not flatten out at 5, 0. Okay, so we can use this information along with the fact that the original polynomial has a multiplicity of 1 and a degree of 8 if we add our exponents. If we multiply out all the x's again, we'll get a 1 x to the 8th. So the degree is even, and the leading coefficient is positive, so that tells us about in behavior. We can actually get a nice rough shape of a graph using all of that. So since the degree was 8, we know that the tails, the end behavior, the tails, both point in the same direction, and since the leading coefficient is 1, we know that they both point up. So we start from the upper left, we come down to negative 3. We know that we just touch and turn around at negative 3. It just comes down and kisses the x-axis there. Goes back up. Has to go down through 5. It has to cross at 5. It does not flatten out. So it just goes straight down through at 5. It's going to have to turn around and go through 8. It has to cross at 8, but it also needs to flatten. So we get this, looks like what looks kind of like an x cubed curve there. Right, comes in, flattens, and leaves. And notice that our tail again now is pointing up, which we said that since it was an even degree and a leading coefficient that was positive, both tails were going to point up. So with this knowledge about multiplicities, we can now state what the Fundamental Theorem of Algebra says. It says every polynomial of degree n has exactly n zeros when you count multiplicities. That's what the Fundamental Theorem of Algebra says. Now, we have to be a little bit careful. When we say it has zeros, it may be, in fact, that these zeros are complex numbers. Okay? So it may be the case that we've got complex zeros, complex roots of the polynomial. But when we get all said and done and count down all of the zeros that we have, it has to equal the number of it has to equal what the degree is. The number of zeros has to equal what the degree is. Again, any root with a multiplicity that's higher than 1, we count that many times. We typically call those repeated roots as well. All right, so going back to the original example, the polynomial has degree 8, and it has zeros at negative 3, 5, and 8, but we are going to count negative 3 twice because that's the multiplicity, and we're going to count the 0 8 times because that's the multiplicity, which gives us the required number of 8 zeros. All right, we've seen already that if c is a 0 of a polynomial, then x minus c is a factor of that polynomial. We refer to that as the factor theorem. If we use this fact along with the fundamental theorem of algebra, we get what's known as the linear factors theorem. And so what the linear factors theorem says is that every polynomial of degree n can be factors as a product of n, not necessarily distinct, of course, factors. Because that not necessarily distinct part comes from the fact that we might have multiplicities that are bigger than 1. All right, we are interested in factoring polynomials completely when we can. Some of these, of course, we've already mentioned that might have complex zeros, so there's one more fact that we need to know to help us out with these things. And this is sometimes what's called the complex conjugate theorem. This says that if p of x is a polynomial with real coefficients, that's actually important. We have to have real number coefficients for this to work. And if a plus bi is a 0, then its complex conjugate, a minus bi, must also be a 0. All right, so let's put this into action. Let's say we want to factor the polynomial 2x to the 5th minus x to the 4th minus 2x cubed minus 27x squared minus 6x plus 10 as a product of linear factors. Now we're also given the fact that negative 1 plus 2i is a 0. So we can use that to know that we already have two zeros. Negative 1 plus 2i is a 0, so negative 1 minus 2i is a 0. So what this allows us to do is go through the synthetic division a couple of times and knock this cubic polynomial down to knock this 5th degree polynomial down to a cubic, a 3rd degree polynomial. We can do that with synthetic division again. Here are the coefficients of our polynomial. The synthetic division here takes a little bit more work because we're going to have to do some complex number multiplication. But we've done that in the past, so I'm just going to go over it. You should check the details and make sure these actually work. Bring down the coefficient, multiply to give you negative 2 plus 4i, add to get negative 3 plus 4i, multiply, you should get negative 5 minus 2i, add, multiply, add, multiply, add, multiply, and add. Remember, we're being told that negative 1 plus 2i is a 0. So when you get to this last column, you have to get a 0. You're told that it is a 0. They're not going to try to trick you. You're told that it is a 0. That means we need to get a 0 down here when we're done. If you know something is a 0 and you don't get a 0 at the end, you've made an arithmetic error somewhere. Go back and find it. All right. This was originally a 5th degree polynomial. We've knocked it down to a 4th degree polynomial. We do have some complex number coefficients in there. So let's do this process again, but use the other root that we know, the negative 1 minus 2i. And again, same process, bring it down, multiply, add, and yada yada all the way through. Again, we know this has to be a 0, so we need to get a 0 at the end. If you don't, you've made a mistake somewhere along the line. All right, so now we've done this with the original thing we told was a 0 and its complex conjugate. Notice that at this stage, all of the coefficients are real numbers. There are no i's left. That's important. When you run the original number through and run the complex conjugate through, you should get real number coefficients here again. If you didn't, you've done something incorrectly. All right. So far now, we've got this down to this quotient. If I go back again, I see the 2, the negative 5, the negative 2, and 2. We've knocked this down 2 degrees, and now we've got a cubic. So now we can use our rational root theorem to help us get the remaining zeros. Factors of 2 are 1 and 2. Factors of 2 are 1 and 2. So if I make all my possible fractions, I'll get 1 and 2 over 1, and then 1 and 2 over 2. So I only have these 6 numbers. Look at a graph. It looks like this graph crosses close to -1, but not quite. So that's not in my list. This looks like it crosses close to 3, and that's definitely not in my list. However, this one crosses at 1/2, it looks like. So we'll try that. And going through the synthetic division, lo and behold, we really do get that 1/2 is a root. The remaining quadratic is going to be 2x squared minus 4x minus 4. We can either try to factor it or use the quadratic formula. This one doesn't factor, so let's go ahead and use the quadratic formula. If we run through the quadratic formula, simplify as much as we can, we end up with the roots of 1 plus or minus root 3. So now we can put it as linear factors. Remember that if a root is a factor, or I'm sorry, if a number is a 0, a number is a root, then x minus that number is a factor. So these 4 here, we got from the 1 plus root 3 is a factor, is a root, 1 minus root 3 is a root, -1 plus 2i is a root, and -1 minus 2i is a root. So x minus each of those is a number. We also saw that 1/2 was a root. Typically we write that as x minus 1/2, but remember the leading coefficient was a 2, so if I take that 2 and multiply it through, I would get 2x minus 1 as my other factor. Let's go the other way. Let's say instead of given as a polynomial and we try to factor it, let's say we're given the zeros and we want to figure out something about the polynomial. So let's say we're being asked to construct a 4th degree polynomial with real coefficients. It has a 0 of 3 minus 2i, a 0 of 2, but that 0 has multiplicity 2, and then it also has a y-intercept of 26. Alright, so since 3 minus 2i is a 0, we know that 3 plus 2i is a 0. So we'll know that x minus the 3 minus 2i and the x minus the 3 plus 2i, those are factors. We know that 2 is a 0, so we know that x minus 2 is a factor. But we also know that 2 has a multiplicity of 2, so that x minus 2 gets squared. I don't know what the leading coefficient is, though. I haven't been told that. However, we are told that the y-intercept is 26, so we can use that information. For the y-intercept, it means we want to plug in 0 and get out 26. So if I do that in this case, we get 26 on the left-hand side. When we put in 0, we'll get a -3 plus 2i, a -3 minus 2i, and then times a -2 squared. Multiplying all of that out, we get 52a, so a must have been a half. So the polynomial in question is going to be 1/2 times the factored form that we had before. And then this would be good enough for me on an exam, just because there's a lot of multiplication you have to do. But if you want to make it look a little prettier, you could multiply it all out and get the polynomial that's 1/2 x to the 4th minus 5x cubed plus 41 halves x squared minus 38x plus 26.